Welcome to my video course on railway safety and systems engineering. When we look at a modern railway network, you aren't just seeing tracks and trains, you're looking at one of the most complex, highly integrated safety ecosystems on the planet. From the interlocking logic processing thousands of variables a second, down to the physical track circuits detecting multi-ton vehicles, absolutely every single component must perform flawlessly. We're going to unpack exactly how this massive ecosystem prevents catastrophe day in and day out, and how systems engineers practically mathematically guarantee that safety over decades of use. Okay, let's dive into this. Today's syllabus is packed. We'll start with an introduction to functional safety, followed by understanding RAM's principles. Then we'll hit the core railway safety standards and unpack safety integrity levels, or SIL. Finally, we'll wrap up with the fail-safe principle and designing for dependability. We are going to build from macro concepts right down to the specific micro standards.
Section 1. Introduction to Functional Safety. Let's define our core topic and what it actually means to keep a complex transportation network secure.
Safety is formally defined as the freedom from unacceptable risk of harm. And this encompasses both system safety, so protecting the actual train movements, and staff safety, which means protecting the people operating and maintaining the equipment. You see, safety isn't just a single product you can go out and buy off a shelf. It's an emergent property. When millions of commuters trust these networks with their lives every single day, true safety only exists when the entire system is perfectly integrated and working seamlessly together to prevent collisions.
Moving on to Section 2, Understanding RAM's Principles. This is the foundational engineering framework that makes long-term safety possible.
RAMS is a really important acronym here. It stands for reliability, availability, maintainability, and safety. Think of these as the four pillars that create total system dependability. What's absolutely vital to grasp here is that safety is just one part of this deeply interdependent equation. A system cannot truly be considered safe if it's impossible to maintain, or if its unreliability constantly forces human operators to use risky manual workarounds.
And this brilliantly illustrates a crucial difference between two concepts that often get confused. Reliability is the probability that an item actually works when required, but availability, that is the proportion of time the system is actually usable. A signaling system could be highly reliable, sure, but if it takes 3 weeks to repair a single minor fault, its availability is incredibly poor, which leads to massive delays and operational friction.
Section 3. Core Railway Safety Standards. Now we're moving into the specific European regulatory framework governing these RAMS principles.
Now, what's really interesting about this slide is how the regulatory standards explicitly separate software logic from physical hardware systems. Because software doesn't physically wear out or break down over time like a mechanical relay does, it requires an entirely different set of techniques for verification and validation.
Let's look at how these distinct standards interact to comprehensively cover the entire life cycle of a railway system. EN 5126 acts as the master umbrella, dictating overall system RAMs. Beneath that, EN 5128 strictly governs the software techniques and coding measures, while EN 5129 manages the safety-related electronic hardware. And it's important to note that these are all heavily informed by overarching global functional safety standards, specifically IEC 6158. They are tailored precisely to ensure absolutely nothing falls through the cracks, from the initial concept all the way through to decommissioning.
Section 4. Safety Integrity Levels, or SIL. Let's explore how engineers actually measure and mandate the rigorousness applied to these standards.
So the crucial point is that SIL is a discrete classification level. It represents exactly how much confidence we need that an integrated system, which comprises both hardware and software, will meet its specified safety requirements. Basically, it tells us how much we can trust the system not to fail in a dangerous way.
The scale ranges from SIL 0, which is your basic integrity, all the way up to SIL 4, representing very high integrity. And moving up this scale exponentially increases the auditing, the documentation, and the validation required during the engineering process. If you want to achieve a rigorous SIL 4 rating, you absolutely must employ strict top-down design methods, heavily verified component libraries, and absolutely rigid change control.
Section 5. The fail-safe principle. This is the historical and practical bedrock philosophy of all railway signaling.
I want you to consider this question for a moment. How do we ensure safety when a system inevitably fails? Think about it. Because regardless of how well we engineer something, hardware and software failures are a statistical certainty over a long enough timeline. Knowing that, we have to proactively design around them.
From the old mechanical interlocking levers of the past to today's modern microprocessors, the fail-safe principle dictates one absolute rule. If an error, a malfunction, or even a loss of transmission is detected, the system must immediately default to a restrictive state. In practical terms, that means turning all signals to red and stopping the trains. The system protects itself by shutting down safely.
Section 6. Designing for dependability. Let's look at the proactive tools and strategies systems engineers use to achieve this.
Let's move to and to see how this builds a strict, analytical approach during the design phase. We start with FMCA, which identifies all potential failure modes and their critical effects. Then we use FTA, or fault tree analysis, to track the exact sequence of events that could lead to those failures. Finally, root cause analysis helps us understand exactly why a failure originated so we can eliminate it. We use these tools to mathematically predict and prevent failure before it ever happens.
Applying those analytical tools leads to some very concrete strategies. We're talking about running redundant systems in parallel, like duplicate electronic interlockings. It means completely eradicating single points of failure and utilizing predictive maintenance through remote condition monitoring. I cannot overstate this. Designing for dependability upfront is vastly cheaper and safer than trying to retrofit fixes into a live operational railway.
Because here is the harsh reality of railway engineering. The operations and maintenance costs will far exceed the initial capital cost of the system. A railway system can easily have an operational life of over 4 decades. That is literally 40 years system lifetime of regret if you get it wrong. The consequences of poor engineering are massive, they're costly, and most importantly, they're dangerous. Getting functional safety right is the ultimate duty of a systems engineer. So the next time you step onto a high-speed train, ask yourself just how many layers of invisible mathematics are keeping you on the rails. Thanks for seeing next video.